You're gonna make us nauseous. Yeah, maybe at the end we'll do a little, we'll do a nice twirl. Okay, are we ready? Okay, terrific. Welcome everyone to 2021 Fall Symposium at SMU. Why the Fall Symposium? Why are we doing this? And in short, this is a wonderful celebration of excellence in research at SMU. This year's program of events, you will hear from participants will hear primarily about research and creative projects from undergrads, but we'll also have a chance you will also have a chance to hear from our graduate level researchers as well. It's an event that we look forward to every single year as we showcase the work of our talented students and amazing faculty mentors and faculty scholars at SMU. Before we kick off this featured panel, I would like to thank partner programs involved today. SMU McNair Scholars, the McGuire Center for Ethics and Public Responsibility, Richter International Fellowships, Hamilton Undergraduate Research Scholars, Cooper McIlvaney Peace and Justice Fellowships, and the Provost Undergraduate Research Assistantships through the Office of Engaged Learning. We are grateful to the people from these initiatives that help make this program happen, including Jackie Lowry, Audrey Richmond, Dr. David Doyle, Dr. Krista Cloward, and Tyler Sungman. Finally, I would like to say a special thanks to Dr. Adam Neal, Assistant Director in the Office of Engaged Learning, who manages all aspects of this program today. Thank you, Adam, for your amazing work. My name is Jennifer Ebinger, and I direct the Office of Engaged Learning, and today I'll be moderating this keynote panel. So today our esteemed faculty guest is Tom Runcevski, and his research team, welcome Dr. Runcevski, that graduate researcher, Claire Lamberti, yes, undergraduate research, Kyle Pecker, and Matthew Heaney. We will learn more about Tom's team soon, but for now I would like to start with the lead of this dynamic team. So about Tom. Tom is an assistant professor in SMU's Department of Chemistry at the Denman School of Humanity and Sciences at SMU. He was richly educated in Germany and Macedonia before coming to California as a postdoc at both Lawrence Berkeley National University and University of California at Berkeley. Using a large umbrella for now, because we'll dive deep in just a second to describe his work, Dr. Runcevski his research lies in physical chemistry, diffraction, and scattering methods again, you will learn about soon. He is joined by his team of 2 undergraduates and 1 graduate researcher. They will have a chance to introduce themselves throughout the program and share their work in the lab, but I want to start with Tom so he can kick off the discussion. So why don't you set us up for today's discussion? And you and I discussed before that there are 4 major work projects that we will explore today. So could you tell us a little bit about these topics or give us an overview of them, kind of the big nuggets? And then could you go ahead and get started and tell us what we should know about Saturn's largest, and these are not my words, most distant, exotic and dangerous world, Titan.
Thank you so much for having us here. As you said, we are working in a very diverse fields, which they all come under the umbrella of physical chemistry. Basically, that is structural chemistry. Our work goes around the structure of materials, which is one of the most fundamental characteristics of matter. The 4 different fields that I will introduce very briefly in a second, they might seem different one from another, but they all have one thing in common, that the structure dictates the properties, and we can learn a lot about that. So those 4 fields that we are very passionate about are, they go from Titan, as you mentioned, Saturn's moon, and I will talk about it very briefly, to fitness supplements that we are very interested in and that can help bodybuilders in the future. Then we can use those fitness supplements to transfer them into deep eutectics and glasses. And finally, something that we started working on recently is antibiotic glasses. So those are basically like the glass you're drinking water from, but made entirely of antibiotic, fully transparent and actually soluble. So those are the fields. And my team members who actually do the work, I don't do anything. They will talk about their own research field, but I can definitely start with Titan.
Okay.
So Titan is one of the places that is super interesting for many reasons, and it got our attention. When I started the group here 3 years ago, it was completely new field of research. And the idea is the following. Titan is, according to me, one of the most interesting places in our solar system for the following reason. It is the only place besides of Earth that has very dense atmosphere. Our atmosphere is made of oxygen, nitrogen, and so on. Titan's is predominantly nitrogen and methane. So the dense atmosphere comes together with a very interesting chemistry. In the stratosphere of Titan, we have a lot of reactions which are going between the nitrogen and methane, fueled by energy from the sun and Saturn's magnetosphere. And all of those reactions on the top are producing chemicals. The chemicals can be methane, ethane, acetylene, cyanide, and so on. So a lot of organic molecules. Those molecules are raining down. So on Titan, there is rain, very similar like the rain on Earth, but it's raining methane. And that methane rain, it's carrying all of those organics on the surface. And on the surface of Titan, we have lakes. Those lakes are not made of water, of course. They're made of ethane. And they are bigger than anything we've seen on Earth. So basically, there is more petroleum on Titan than in the entire Earth in just one lake on Titan. So all those chemicals are raining down, and also they're later evaporating. So we have a cycle. So we have a cycle of organic molecules, very similar to the cycle as on Earth. Mm-hmm. We have solids, we have liquids. Basically, we have all of the conditions for life. We are not saying that there is life on Titan. Absolutely, we don't know that. But that's the reason why NASA will send the next mission, the Dragonfly mission, which is planned to take off in just a couple of years, and it will arrive on Titan in a couple of decades to explore the possibilities for life on Titan. So where do we come with our research? Exactly. On Titan, as I said, there are a lot of organics. The temperature on Titan is around 93 Kelvin, which is quite cold. The atmosphere is the pressure is 1.4 atmospheres, very similar to Earth. Now, under those conditions, only nitrogen, methane, ethane, and propane will be liquid or gas. Everything else would be solid. Mm-hmm. So for example, benzene, for us, is just a common chemical, but on Titan, it's a mineral. And all of those organics on Titan are actually minerals on Titan. They're naturally occurring minerals. What we are excited about is to figure out the structure of those solids. Again, the structure of benzene is not very important for practical applications on Earth because it's just a common solvent, but on Titan, it's integral part of that world. And if we want to learn more about the possibilities of life or overall the structure on Titan, we definitely need to know more about those materials. Mm-hmm. Now, what is quite interesting to me is that we know very little about those simple organic molecules. When I say benzene, when I say acetonitrile, those are one of the most common solvents on Earth. Arguably, we can find them in every possible laboratory on Earth. I don't think there is any chemical laboratory that doesn't have benzene or acetonitrile. Those are the two most commonly used solvents. The fact that we still can discover something new, and for example, we discovered that they self-assemble in a unique co-crystal that is stable under conditions of Titan. Mm-hmm. I think it's quite remarkable that in the 21st century, we still can learn something about the fundamental nature of the two most common solvents on Earth. So that was one of our first discoveries, that benzene and acetonitrile, under conditions of Titan, and of course under conditions on Earth, if it's cold enough, they would form a unique co-crystal. So why this would be important? This actually solves questions that NASA had for a long time. For example, one of the questions that can potentially be solved is detection of minerals. On the surface of Titan, only benzene has been unambiguously detected. We know by the spectroscopic signature that benzene is there. Acetonitrile is only tentatively detected, so we don't have a very strong proof that it's there. One of the hypotheses that we have now and we're testing is that we cannot see acetonitrile because it makes this co-crystal that we just discovered, and that co-crystal will have slightly different spectral signature. So this is one of the applications that with our modeling of Titan on Earth in our lab, we can give some information that can help the million-dollar missions like Dragonfly or analysis of the Cassini-Huygens data that has been going on for over a couple of decades now. So this is one of the projects that we are very, very actively working on, and we recently started collaborating with NASA, and we summarized these discoveries in an account, which is a way of a review article that is talking about the possibilities of different minerals on Titan. So this is one of our research areas.
It's really exciting, and I guess, like you said, I mean, there has been a lot of publicity recently, and I was noticing that hold on, with these, it's been circulated like throughout the world, and with The Economist. I guess Economist is one place that you've been. Is it Economist?
Right, there are a couple of
places where they're featuring this.
Right, so I mean, this is one of the topics that is quite interesting to the general public as well, because it's Titan is an interesting place. So a couple of media shared our story. The Economist, Wired, CNET, a couple of other places.
So it's like a 65 million potential viewers. Why are they reading it? Why do they care about it so much? You know, from layman's perspective. And I'm just so curious too, like, what does that mean for SMU? How does, you know, I mean, that must, to get on the radar like that, you know, that's
right. I mean, people are interested about space, and I do think that Titan will become the big next place in space. Traditionally, we first went on the moon and we discovered a lot about the moon in the 60s. Then the next frontier was Mars. We discovered so much about Mars. Now, I think Titan would be the next big thing, because in a couple of decades, because NASA is sending a mission there. The mission will arrive and it will spend a couple of months detecting what is going on Titan. How is the structure? Whether there is something going on that moon. Our experiments are providing a glimpse in the possibilities on Titan. And of course, we cannot for certain say that we will see exactly what we see in the lab, but it will be very interesting if our predictions help actually the NASA mission. That's the reason why I think it's important. People are interested because still it's a very strange world. I mean, we have lakes of ethane, we have storms of methane, and it's so cold, yet there are so many possibilities for actually life on Titan. That in my opinion, that's the reason why people were quite interested. Speaking about,
because there's life, potential for life.
There is a potential for life, and we can debate it whether there is or not, but arguably there is. For example, one of the material that exists on Titan is acetylene, which is a small molecule with unsaturated hydrocarbon. We have bacteria on Earth that live at very harsh conditions, and they feed on acetylene. So they survive purely by eating acetylene. On Titan, we have liquid ethane. We have acetylene dissolved in that ethane. Technically, we could have a bacteria very much alike on Earth that feeds on acetylene and survives anaerobically. Of course, we don't have any proof that it exists and that evolved on Titan, but technically we do have a possibility for a life very similar to the one that we have on Earth under certain conditions. All of this are speculations, and by no means we are saying that we will see exactly that. But whatever we see about Titan, everything is interesting because it's a world that is so different, yet so similar than the one on Earth. It's a very unique place.
Yeah, it inspires. It inspires the dream. You know, like with just when we were chasing after Sputnik, and to inspire discovery to inspire imagining life a different place, or even how we could adapt, right, over time as our planet changes.
No, absolutely. Also, all of this research is very transferable to Earth.
Yeah.
We do not, of course, we don't have those temperatures on Earth because it's warmer. However, in physical chemistry, temperature and pressure go along. So if we have high pressure and high temperature, we'll have very similar behavior sometimes in the phase diagrams, we call them phase diagrams, as if we have a low temperature and low pressure. And I'm saying this because very similar chemistry can happen on our petroleum deposits on Earth. And we can see very similar chemicals on Earth in the petroleum deposits, which can inform extraction of natural resources like oil, natural gas, and so on. So in that regard, it's also this knowledge is transferable in life on Earth as well.
It is super exciting. We're going to circle back to the second question that I have, because I'd love to hear some more about the other projects. And you all should know there's a reason why I'm moderating today, because it's important to have layman questions instead of highly technical questions, so that, as they talk about this at the depth that they do, that folks like me who are like, well, what does that matter to people? Or does it matter at all? Can ask those questions so that we can hear about those possibilities and connections too. So thank you for your patience with those simple questions, but probably the questions that inspire the 65 million people that are viewing in and really curious about this. I'm super curious about this now. So let's go ahead and let's transition here. And the second research topic is completely led by an undergraduate assistant and Hamilton scholar, Kyle Pecker. Can we go ahead and pass it off to him now?
Absolutely.
For now? Okay. So Kyle, can you share a little bit about yourself and then tell us about your project that revolves around fitness supplements, sports, and bodybuilding?
Of course I can. My name's Kyle Pekar. I'm a senior currently, double majoring in chemistry and biology. And I became involved in undergraduate research here at SMU in my freshman year. I was lucky enough to have a faculty in residence who was a chemistry professor. He's actually here right now, Dr. Sun. And he was able to put me into connection with several different chemistry groups in the department here at SMU. And I spoke with many of them, but Tom impressed me by far the most. And at the time, he had several different projects that he could possibly give me to work on. And one of them that appealed to me was creatine. Creatine's one of the most common supplements used in the athletic world. It makes hundreds of millions of dollars in the US annually. So as you might guess, if you ever walk into a gym, somebody in there has probably supplemented creatine at some point. And with that knowledge of how relevant it is, we decided at the time to take a look at how it was being formulated and marketed. And what we found is that there's only two formulations on the market currently. The most commonly sold one is a monohydrate. So it's just creatine with a water molecule. And because of that, its solubility, or its ability to dissolve in various different liquids, most commonly water, is actually relatively low. And so with that in mind, if we're able to improve on that in some sort of way, we would have a significant impact on the industry. And so we decided to set out to try to increase the solubility, or increase its ability to dissolve. At the same time, we actually found another supplement that was available, which was a hydrochloride salt. And so when they developed the hydrochloride salt, the reason that they did that was because it would be more soluble. So HCl is a really polar molecule. You don't have to know much about it, but it's an acid. And so it's making the creatine dissolve a lot easier when you put it into a liquid such as water. So with that in mind, we took a look at the HCl, and we also found there that there was another issue, which was that it was highly acidic because, as you might guess, it's got the acid packaged in it. So we identified two problems at the time, which were a low solubility and a high acidity. And we wanted to find a perfect medium between the two. We wanted to increase the solubility, but at the same time, not drastically increase the acidity as the HCl had done. So in my freshman year during the winter break, I spent around 2 weeks, and we went through a thorough screen of various different ways to prepare creatine. And as Tom has already mentioned, one of those ways is as a co-crystal. And so a crystal is just a solid and it has these repeating units. You can imagine a bunch of blocks stacking on top of each other and making a big building, for example, and all the blocks are the exact same. A crystal is sort of a lot like that. And a co-crystal is putting two different things inside of one block, basically. So with that in mind, we wanted to pursue a co-crystal that would exactly achieve what we wanted to do, which was, again, increase solubility, decrease acidity. So during the screening, we went through hundreds probably of different counterparts, and throughout all of them, we found that only one of them actually produced a co-crystal. That was citric acid. And we looked at different salts and other different types of formulations that weren't co-crystals that could potentially increase the solubility and acidity. But we found that this one was particularly appealing because through our characterization methods, and there's a variety of different ones, but we can look at how the co-crystal decomposes, we can look at how it dissolves, we can look at how it organizes in different temperatures and pressures. We can look at a lot of these different things. And what we found was that creatine with citric acid has a 3-fold increase in solubility while having a 10-fold decrease in acidity. So these are drastic improvements on the current formulations that are available in the market. And obviously, this is summarized in a few sentences, but this was actually a very drawn out process of various different experiments. We had to, you make one small discovery and then you have to pursue that a little bit more and see where it goes. And in doing so, you might find something new. And that's the beauty of research, is the intellectual curiosity that comes along with it. And we were just so lucky that whenever we found this co-crystal, it was actually such a drastic improvement. And so with
us a little bit more. I know you can't say much, but can you talk to us a little bit more, you and Tom both, please jump in, about the significance of this for not only your work, but also for the university, and why it's important as we strive to this Research One goal as a university? Why these types of opportunities and these successes are so critical?
Of course, we can speak to that. So the patent that we were able to file, it basically patents the method of the preparation of the co-crystal. So we looked at the time, whenever we discovered what was happening with citric acid, we looked in the patent database and found that there were actually patents previously with citric acid and creatine. And we went through the experimental procedure behind those. And what we found was actually that their method of preparation differed significantly from ours. The way that we were able to obtain a co-crystal was through mechanochemical synthesis. And this is vastly different than, the conventional solvothermal synthesis that a lot of people imagine whenever they hear about chemistry, which is, just throwing some stuff into some liquid and stirring it around and some color changes. This is vastly different. Mechanochemistry involves the physical impacts in a different type of milling and various different types of milling instruments. And as a summary, the way it works is that you have a milling capsule and you'll put your materials inside of it, and it seals, you'll close it and it seals. And along with them inside, you have to also put a milling ball. And you'll secure the milling jar with the ball and the materials inside. You'll secure it into a milling instrument. And whenever you do that, you secure it very tightly unless you want to accident. And it'll shake around very, very quickly and rapidly. And as it's doing that, what's happening is the ball inside is striking the inside of the capsule very hard, and it generates incredibly high temperatures. And that's exactly what's needed for formation sometimes to occur of different materials. So our method there, whenever we use that for producing the co-crystal, it actually yielded complete conversion of creatine and citric acid into the co-crystal. This is significantly different from the patents that we saw previously on the market, which, like I mentioned, use solvothermal techniques. Whenever we reproduce those on several different instances, we found that every single time, what it was actually producing was a mixture, a physical mixture of pure creatine, pure citric acid, and some of the co-crystal. And so what that essentially means is that you have a loss, right? You don't have full conversion into the co-crystal, and that's not what industry wants. Industry wants to be able to have an efficient conversion so that they're not wasting any materials. So because we saw that difference, that's very significant. And we were immediately interested in pursuing a patent that might lead to commercialization. And that's exactly what we did. And we've, I can't, like you said, reveal too much, but we have significant interest in the patent, and it will likely be leading to commercialization in the coming years. And that's incredible for SMU, because what that means is that a supplement formulation came from this university. And it's not just any, small supplement that, you might see one container of in a GNC store or something. You walk into GNC and you'll see shelves of creatine. And so if this formulation proves more appealing, what that would essentially mean is that we've significantly altered a $350 to $400, $500 million market annually in the United States. And that's just incredible for a lab to be able to accomplish.
So one of the, as Kyle said, this is a major discovery. What needs to be mentioned is that our research in this field belongs to the so-called enabling technology. So creatine and citric acid has been known that it has been predicted they would form a co-crystal and that can be used. However, that has not been proven up to now. We provided the technology, how we can get to this co-crystal, and we also provided the characterization tools. And that enabled this technology to develop. And actually, we signed the licensing agreement yesterday. So thank you. Very soon, the university will be able to communicate it to the public and advertise it. The reason why our group was able to push those limits, and again, we are talking about materials that have been studied intensively so far, comes to again what I started at the beginning with structure. As Kyle mentioned, this supplement is being produced mechanomechemically. That means we have milling. Whenever we have milling, the crystals are being quote unquote powderized, and we have powder. So for those who are not experts, to figure it out the structure of materials, if you have a single crystal, it is relatively easy. And today that's very straightforward method. Actually, it's very at the level of service. So you give the single crystal to a service facility and they give you the structure back. That is completely fine. But whenever you have it at powder, those are still crystals, but those are, let's say, billion of crystals in just one vial. And it's incredibly difficult to separate them and just to study one by one because they're so small. Our group is one of the few in the United States, and I would say one of the around 30 groups in the whole world that is able to analyze the structure of pretty complicated materials from powders. So we are talking about, in layman terms, solving the crystal structure of billion samples at the same time.
Yeah.
That comes with a lot of reduction information, a lot of problems in the data analysis, but it's absolutely possible. So that is where we made difference. And I'm sure that in the future we can find the next creatine and the next sample to go and to analyze. It gets even more important when it comes to drugs, because one of the reasons for a lot of pending patents and pending approval from the FDA is the lack of characterization. If certain material is not thoroughly characterized, it cannot be commercialized when it comes to drugs, for example. That is a space that we can make a very big difference. 90% of the pharmaceuticals are in crystals currently. Out of them, a lot of them are with unknown structures. Every new structure, every new polymer is a patent on its own, and it comes with its own stability, with its own bioavailability, with its own applications. So all of this research can be extended not only to supplements, but also to drugs, fungicides, pesticides, and pretty much many other parts of material science.
That's what, for those who are not involved in research, I think that's one of the exciting results, right? Knowledge, building upon knowledge, that it is a process, and everyone's playing a role in increasing our understanding of a field of study or a phenomenon, or so, and I think that that's really interesting. It's happening very naturally in your lab. Probably it sounds like the way you work is like this, is that you guys, you uncover every stone, and once you have hit saturation, you're like, wait a minute, there's someplace else to go here. And I think that that's really where your research comes next. And so I really think that this is a great segue. I understand that you're working on a new class of solvents, probably found because you had discovered something. Was it you had noticed something in Kyle's work? Is that how did it happen, the transition? Yeah.
The way the transition happens, I can put it in this very simply. We get bored to work on just one thing, so we try to go in every direction. So far we spoke about crystals. So far we spoke about order and solids, but we got a little bit bored with that, so we extended to the completely opposite direction, which is molten state and liquids, and Matt is really an expert in that field, so he can take over.
So Matt also is a undergraduate research assistant and Hamilton scholar like Kyle. So yeah, tell us a little bit about yourself and share your work.
Yeah, sure. So I'm a chemistry major, geology minor. I started in the group about 2 years ago when I transferred here as a sophomore. I'll be graduating in December, so I should be a little bit early, which is great. But I'll be sticking with Tom for spring semester at least, so I can at least finish some of my other work with them, and I'll have more time to also work on it without outside classes. But yeah, with my work, as Tom stated, it kind of came out of what Kyle's research did. So ours is on deep eutectic solvents, specifically one with creatine and citric acid, just like Kyle's work using creatine and citric acid, except ours, in the way we formulate it, forms a liquid and can be used as a solvent. And specifically, it's a deep eutectic solvent because of a certain set of properties that has. All deep eutectic solvents are liquid below 100 degrees Celsius. They're environmentally friendly or green, and they are relatively commonly made with usually available chemicals. One of the most common ones is urea and choline chloride. Most people probably don't know what the last one means. They probably know what urea means. Probably not pleasantly, but
it's natural.
Yes, it's natural. And so with the creatine citric, The interesting thing that we have is of viscosity, everything moves so slowly that it has to kind of move, that it has enough time to move into a specific orientation that works for it and won't cause it to break. And that's actually beneficial too, because we have been able to actually show a variability in the viscosity over temperature, which is quite common. If you've ever had really thick syrup at like a diner or something, it'll come to you and it's usually kind of wet and warm, and that just makes it easier for you to pour it on like your pancakes, your waffles. And the same thing is sort of seen with a deep eutectic solvent and many other things that are very viscous. And with ours, it also works in the reverse direction. If you cool it down, it gets a lot thicker. And at a certain point, when it gets cold enough, it actually undergoes a different kind of phase transition from typically like water turns into ice at 0 degrees Celsius or 32 Fahrenheit. Ours at like 280 Kelvin, which is just above just above freezing point of water. In some cases, we're able to get it to undergo a glass transition, and basically it just goes from being a liquid to being a sort of a solid as well. Basically, it's turning into a glass via vitrification, which is the more scientific term for it. But it's maintaining a completely disordered structure. So all the molecules are in complete disarray. They don't really have any set way that they're trying to align like they would in a crystal. And that provides a unique environment in the factor that nothing is going to be really causing them to form in one direction. And that's a problem for proteins too, because when you freeze and thaw a protein, what ends up happening is that usually water crystals will form and they can actually grow into a protein and basically pierce it. And then obviously your protein chains can be broken up. And that's actually partly what causes freezer burn taste on foods. If you've warmed or thawed something and then frozen it again, or if you've kept it in the freezer too long, it has that bad taste. And that's because the proteins inside of a meat or something have been severed and it doesn't taste quite good. And that's a common issue. So with a completely amorphous substance or completely disordered substance like a glass, you never have that sort of orientation of any of the molecules. So you can actually bring something down to a low enough temperature that it stays inside that glass state. What's also beneficial for that as well is that since we can get it above a certain temperature to, let's say, just at 0 degrees Celsius, we can keep it in a glass state where stuff is basically solid. If you were to put a protein in there that is normally only stable to like -80 degrees Celsius, kind of like the COVID mRNA for vaccines. What you actually can do, and we haven't tested this because we're not really into biochemistry, we're into physical chemistry, but if you can bring it down to the temperature where the mRNA for a COVID vaccine is stable, then you can put it inside the deep eutectic, which is going to be glass, and then you can bring it up to a temperature that it's still glass at, but won't cause any sort of like dissociation of the protein or cause it to break down, which is a common problem for storage and transport of it, especially to poorer countries. And that also falls into also drugs as well, stable drugs.
To what
Yeah.
you were describing. It's the potential for this to actually influence the quality of drugs and how they're being
Right.
manufactured. And
So this type of
sorry, I just wanted to.
no, this type of materials have different applications. So what Matt said is absolutely right. So we can use them as a drug delivery vectors, as a virus delivery vectors, deep eutectic solvents, and ionic liquids. That's another class of materials. They've been used as a green alternative because as an alternative to solvents, because they don't have vapor pressure, they are non-flammable. So a lot of effort have been directed in the last 3 decades in that direction to make this materials green. And there's a lot in the literature done in ionic liquids and deep eutectics. However, most of the materials that are out there as ionic liquid, that's a huge field. A lot of people, thousands of people work in that field. So most of those materials are made of toxic chemicals. So in our understanding and in our strategy, we don't want to create green chemistry with toxic materials. We go in a direction of making deep eutectics that not only are non-toxic, not only that they're very benign, but they also carry nutritional value. Creatine is a supplement, as we discussed previously. Citric acid, and we can make it with other materials, are provitamins, and they also carry nutritional value. So not only we create a deep eutectic solvent similar to ionic liquid, we create edible deep eutectic solvent. We can also use it as a drug delivery vector, as I said. So there is a lot of potential for commercialization here as well.
And while we haven't tested it yet, I'm certainly willing to test it at some point. I'm fairly certain that it will taste quite sour. I haven't gotten a hold of any food grade reagents of creatine and citric acid yet, but I'm definitely planning to in the future. So definitely on a follow-up paper from our one that we're going to be publishing by probably the end of this week, correct? Yeah. We'll definitely include our palatability results.
Well, I faith, like I said, last time I talked to you, you're like, this tastes terrible. We got a lot of work to do, so obviously.
I beg to differ in that because
No, this was a long time ago.
we actually one of the materials that goes to the production of sour candy
Oh, you like the, yeah, right? Like
goes
the
with tartaric and
sour
citric
patch Kids
acid,
and
Yes.
stuff like
right?
that?
So that's up to taste.
I guess so,
Yes,
yeah.
yes.
Yeah, I don't mind sour, so it wouldn't, but it depends on how sour it is, right?
Yeah.
Like makes your ears.
But
hurt
also
and
here
stuff.
we are not talking about having a material that will completely be eaten pure.
Yeah, but
It's also an
Safe.
additive and can be added in a very low amounts that will have the benefits,
Right.
but will not be as sour. Those who really like sour, they can eat it. But I mean, we haven't
That's not
tried.
the ultimate goal,
right.
but
Right,
It's
we
a
haven't
solvent.
tried it, but we don't have the food grade chemicals, and we adhere very, very strongly to all the safety rules
yes.
in the chemistry book. So, but that's something that is part of commercialization. So the company will take care of upscaling and also clinical trials and palatability and stability.
Right. Well, so this is so interesting. I think we're probably going to go over time, but I want to make sure we have a chance to talk with Claire as well. And I'm actually, Claire, you are just moving and shaking in your career. And I don't think I would do it justice to really brag about the type of awards you've received and the type of work that you are embarking upon. So I'm going to pass the introduction on to Tom, because I'm afraid that you probably wouldn't, maybe you might not share what should be shared about you. So can you brag about her for a minute? before she
Absolutely,
starts?
absolutely. So in our group, we pay a very, very close attention on the success of our students, graduate and undergraduate. Most of our undergraduate students are Hamilton Scholars, as we have them here, but we also have the equivalents in the graduate part. Claire is one of the few grad students at SMU that won the NSF GRFP scholarship, which is the most prestigious award awarded by the NSF National Science Foundation for graduate researchers. Another group member in our group has the NASA equivalent. So we do pay a lot of attention to that. It's very important, and Claire that definitely deserves that. And that's not only an award she has, she also won the SURF Fellowship by our collaborators in NIST. So she spent research at the National Institute of Standards and Testing. And she's taking off very, very strong with making antibiotic glasses, but unlike any other glasses. And I will let her talk a little bit about it.
Well, thank you. So basically, when I joined Tom's group, I came to him and I was like, I want to do something that's different, that's unique, but also very challenging because I love challenges. And one of the things that we decided to do was start a new project. And we took a look at the WHO, or the World Health Organization's list of model essential medicines, which is basically the list of medications that are most commonly used by the most people in the world. It's a very comprehensive list. It covers everything from broad range antibiotics to tracing drugs and things like that. So it's a very, like I said, comprehensive list. And we took a look at the list and we determined which drugs did not have solved crystal structures and or had poor solubility. And we were like, okay, we're going to find a way to not only solve the crystal structures of these compounds, but also to improve the solubility and stability of them if we could. And so we found a class of drugs called cephalosporins, which are a very broad range antibiotic class that a lot of people use worldwide. And we came up with a bold solution to essentially stabilize the drugs in the form of a glass. And that kind of was springboarded by the work that my colleagues have done, where it kind of formed a glass using their materials. And so we were like, okay, we're going to try to apply that same concept to our materials and see how that works. And so that's exactly what I've done. I've put multiple broad range antibiotics into the form of a glass, and we're looking at the solubility and stability of those compounds. We know it's a glass from the glass transition that we see upon heating and cooling when using our differential scanning calorimeter, which is basically what they're talking about with phase transformations and transitions. That's the instrument we use to determine those. So we've proven that it's glass. We proved that the drug itself is stable in the glass up to formation and annealing, which we heat the glass and see if the drug will remain in its chemical form or if it'll decompose. So we've proven that the glass via NMR stabilizes the drug even when annealed up to 80 degrees, that is. But yeah, these drugs very well seem to be stabilized in the glass, and they are drugs that frequently decompose upon access to light or heat. That's a very big problem that they have, is that they will actually decompose and no longer be viable as drugs. So stabilizing them into something that we don't have to freeze, which is where they have to be stored, is very important. And we don't have to freeze the glasses. Up to this point, we have not frozen the glasses. We haven't put them in the fridge. We haven't done anything to them. And we still see stability, like I said, up to this point. So
I mean, it is truly, it is groundbreaking and,
So-
and really, really exciting. Because that is the dilemma that, I mean, it's staggering to me, you know, that we throw away so many of the vaccinations. There are countries, my father and mother-in-law, they live in Guatemala half the year, and they're struggling to get enough vaccinations. And part of the problem is number that they can afford, but also them transporting it, and a lot of them going bad before they actually are able to be used. So this is just so exciting and
So with the
world changing.
with the antibiotic glasses, it's we are very excited, and we cannot share more now because we are working on it.
Yeah.
But what we can say about this project is that it's one of those projects that we know that we are successful, but we don't know how much, because we definitely made 100% antibiotic glass without any additives. Sure, glasses exist in formal antibiotics, but they're mostly with additives.
Mhm.
This is 100% only antibiotic. We can also load it with many antibiotics. We will load it so far with 6 different drugs, and it's still
all in
glass,
one glass.
all in one glass. But what we really are looking now, before we decide to communicate to the public, is the stability.
Yeah.
We do believe that we also see some preliminary data, still yet preliminary, that we have increased stability. And this is important because we are not talking about some obscure medicine that no one is using. We are talking about one of the most prescribed drugs in the world, not only United States, but throughout the world. It is absolutely one of the most. I think that for one class, subclass of this drugs is it's 16% of all pediatric prescriptions for antibiotics went to that part of the subclass.
Mhm.
If we achieve to make it 8% more stable than it is, or to raise the temperature of storage, that would be a really nice, really groundbreaking discovery.
It's amazing. I'm in awe of the work that you all do. It's super exciting. And like I said, from Titan to the glass, it's just, it's inspiring. It creates hope, and just this, it sparks imagination. And as humans, we love that. And your creativity and your discipline and your curiosity is just amazing to me. And this has been fun. Well, I'm going to close. So because we should, although I don't want to, because I have so many more questions. But maybe we can do this after, you can go public. We can do this again when you go public.
Absolutely.
So I guess that it close, I know that there could be opportunities for us to talk about some other work that you're doing. I know with pigments and pigmentation, and those in the arts might be interested in it. So if you're listening to this and you want to hear about that project, then, write Tom and see if you can get him on the speaking circuit.
Actually, when it comes to pigments, they should write Matt, because he's getting a paper ready
Yeah.
that should be published very soon about 2 very common pigments. So all the questions should go to him.
Well, okay. So when you're done with it, let us know so we can put it on our website so people can access that for sure. Go ahead, John.
We'll definitely have some very good pictures. I mean, I know Tom's Twitter banner for the longest time has been one of the pigments.
Yeah. Oh, really? I didn't
Yeah,
know that.
they're beautiful.
See?
The crystals are just the most beautiful red color, and we are at SMU. Red is our color, so
Yeah.
of course we went with a red pigment.
You celebrate, but they didn't know it's that special red, right? It's not Mustang red. It's the red.
Yeah.
The red from, I guess you can't tell us from the origin of the red.
Not
yet, okay.
really. I
Okay.
mean, without giving it
Okay.
away.
Yeah.
which
Let's don't
one
give it
is,
away.
yeah.
Let's don't give
It
it
should
away.
come in the next 2 months. I would
Okay,
say. Yeah.
okay. I love secrets. So just in close, this is again to celebrate research here at SMU. So, there might be people that watch this and don't know about it or don't know why you want to get into it, but can you just share just real quickly, like why this is important, why other people might want to do this? And I'd love to hear too what you're going to do next. So
Go first.
yeah, just kind of
I think
pitch research.
research is just fantastic for especially developing just critical thinking. And as I've mentioned earlier, intellectual curiosity. And also, as you've mentioned, discipline. All of these things are all melded into or meshed into one whenever you're researching, because all of them are, being invoked as you're working in lab. You have to be concentrated, but at the same time, you have to be wondering what you should be doing next, what could come from the results that you have. That's the kind of hypothesis formation that is characteristic of pretty much every lab in the world. And because of that, those skills aren't only limited to research. They're incredibly important as well in just your everyday life, the ability to have, strong discipline, to remain curious, to learn more, to be able to critically think and solve different problems and issues that you're faced with in the modern world. All of these skills all come into one and are developed in a research lab. And I would argue very effectively. I would say that myself, I've seen a significant development in my ability to, challenge different thoughts and be able to solve different issues as they arise.
With tenaciously
Yes.
solve it. What do you imagine that are you planning to go on
Oh, yes.
in a career?
Yes, I will be applying to graduate school, and I'll be pursuing a PhD in chemistry. So I'll be applying right now. And I hope to be able to continue to develop those skills that I've spoken to, and in the process to improve the world around me, and do so through the power of the universities that I'm at.
Okay.
Yeah, so I mean, kind of basically off of what Kyle said, basically research has been sort of like a way of applying what I've learned almost. I was kind of a weird child for one thing. One of my hobbies was hobby chemistry. So research was almost like a better outlet for me than working in my family's kitchen with various chemicals that probably shouldn't have been working with. There are a lot of stories to be told there, but
unsafe.
yeah, it was
You're
unsafe
keeping them
sometimes,
a
but
lot more safe than he was in his kitchen, clearly.
yes, there's a lot more equipment that's better suited than just open windows. A fume hood is definitely better, but it's definitely been, at least for me, a better idea of like a sort of creative outlet in that regard. Like it's actually a way for me to be able to explore my own hobby, but also as like an occupation as well, which is kind of almost living the dream for me. And it has been in that way for me. I certainly think that there's other people obviously like me that think that same way. And I know there are, but the vast majority of people probably don't speak to that at least the same way as I do. But it's definitely outside of that a great way for me to see like what I've learned in my classes put into action. I probably would not have done as well in PChem 1 if I had not done research with Tom, especially on like the second like section of it where we started talking about phase transitions. But it's definitely an interesting feeling to like see something that I've learned in one of my classes. I was like, oh, that won't be of any use to me. And then seeing is that like exact situation come up in my research and be like, I remember learning about this in PChem or in OChem or whatever. And it's constantly like a weird sense of how interconnected science is. Even in my geology classes, I've been able to find a very interesting connection, especially with crystallography, which is, I mean, just study of crystal structures. And that's been kind of, it's been really view changing for me, because now I don't think I see stuff the same way as I used to, as that scientific fields and all my subjects were inherently like sort of disconnected. They're all very much connected.
Synergies between
Yeah,
all.
even weird classes I've taken, like like a digital literature class I've found as being useful for like data science, and has been incredibly helpful for me making figures for papers, because I know not everyone in our group uses the software we use for making our graphs and stuff. And I've learned different ways of being able to apply that, or at least programming, and sort of understanding what data itself is, and on a deeper level. So it was kind of interesting to me. And now every single time I see something or I learn something new, I'm like, how can I apply that to my research work that I'm doing, and how could I make my life easier?
So what do you think you're going to do next?
Like with Kyle, I'm going to be applying to graduate school, and I'm going to be pursuing a PhD in chemistry, specialization in radiochemistry, which is chemistry of radioactive materials.
Exciting. Now, so I kind of should flip this on it. The question for you a little bit on its head, because you've arrived, right? You're doing your PhD, you're where they aspire to go. And I'm just curious, what is it like to have to be working in a lab where you have graduate students under, Tom's direction? What is it? Because I don't know, did you have those experiences before when you were in undergrad, or how did?
So I did undergraduate research at my institution before I came here.
Where were you at?
I was at University of Texas at Tyler.
Yeah.
And so I did research there in instrumental analysis chemistry and physical chemistry. So I basically had those experiences. I didn't have experiences with graduate students in the lab. It was only undergraduates. So that
You guys are
has
lucky.
really,
Yeah, they're really lucky.
it
But
really,
now it's
yeah.
like, then you can imagine what it looks like, where your pathway, because
Right. It's
you've already had these
definitely an
experiences.
advantage that I wish I
Yeah.
had, you guys.
Yeah.
But it is really nice because I'm always learning something from them. Like I'm always learning from these two, especially, and learning, how to do things in the lab and how to do specific processes that we have in the lab, and how, because they've been here longer than I have, and so they've been through all of that. But I hope that in some ways that I can also show them that, hey, it is possible. It is, I was also a nerdy little kid who did chemistry as a hobby. So,
You're making it your career.
yeah. So the fact that you can transform that into, going to get your PhD in something that you love, which I love physical chemistry. I want everyone out there that thinks that maybe they're not smart enough to do it, or maybe thinks that they don't have the experience to do it, that you very much can do it. That it's not something that should be that there should be gatekeepers for, that it's something that should be accessible to everybody who thinks that they want to pursue it. Yeah, that's what I think.
It's a great mentor perspective, and so gracious, and it's going to be great when you're in Tom's seat, because you'll build that culture in your lab someday too. So thank you, Claire. So Tom, go ahead and close it up. So any last thoughts? You can say whatever you want.
Yeah, no, I know I
Close it
can
whatever
say,
you want.
I'm one of those people who says whatever.
I know.
I do not have very much of a filter, but I do know how I want to, what would be my last words for this panel session. It will be to say thank you to your office for all of your help since day number one. Engaged learning really helped us, and we really appreciate you. So that I will finish with that.
Oh, well, thank you. Thank you.
You're more than
It
welcome.
is a real privilege to know you all, and to watch you all on this journey. Thank you so much for sharing today what you are doing. Again, I am fully inspired. I am in awe, and it's just absolutely remarkable. We're so lucky to have you driving us to this Research One goals, and modeling what that looks like, and creating these mentoring experiences, and changing a lot of things in this world with your discoveries. So thank you very much. This is really a privilege to moderate today. So
Thank you.
all right, thank you very much. Cheers.
Thank you.
mean, we can questions in later. But you probably have to go too. Well, that was the problem. I'm just like, should we have David do this? And I'm like, no, he'll ask so many questions. We won't be. I'm like, you need somebody who doesn't know what questions to ask. Thank you very much. No, thank you very much. Do you guys, how do you feel about it? Do you feel good? Do you feel like you had a chance to share to the world your work? Yeah, so what we'll do is we'll produce it and we'll put it, we'll have it, we'll give you guys a chance to see it and we can, add pictures into it and stuff like that. But hold on, let me do this. Hold on. All right. Just don't want to lose anything. Meeting.